Dr. Kate French is a research geochemist at the Central Energy Resources Science Center at the USGS here in Denver. She got her PhD from MIT Woods Hole Oceanographic Institute and specializing in chemical oceanography in 2014. Her research expertise is in organic geochemistry, specifically molecular characterization of organic matter preserved in sediments. And her research emphasizes improved analytical methods and better understanding of how to interpret biomarkers in the sedimentary record. She's quite an expert on the organic matter and even consulted with NASA on the contamination requirements for the Mars Sample Return Program. So quite exciting to have Kate here. As a reminder, we have a chat box, and so if you can please type in your questions to the chat forum, and then I will go over the questions and read them out to Kate at the end of the presentation. But with that, we'll turn it over to you, Kate. You there, Kathy?
Yeah, I'm here. I'm just
sorry.
Looking through all my windows. So yeah. Bear with me for a second. All right. 1 second. This went a lot more smooth in the practice round, but I will get it.
There's no sweat. My computer just went through some updates too, so it's running a little slow as well.
Let's see. All right. Let's do this. Have I shared the screen yet? No. All right. Here's the shared screen. That's good.
Yep, that looks good, Kate.
Okay, well, we'll just do it like this then. I'm missing one of the windows I usually get, but you can see the screen. Can you see my cursor on the screen?
No.
All right, let's see what I can do to change that.
Kate, it was there, it was just tiny.
Yeah, I think the cursor would be useful if we could figure that out.
Oh, it is tiny, I see it. Yeah.
I'm gonna do the share screen too. Yeah, I don't know. It's different than what it was, of course. So anyways, but you can see the cursor. It's small, but you can hear me, you can see me, and you can see the shared screen, right?
Yes.
Then I'll get started.
Okay.
So my name is Kate French, and I wanted to thank you for inviting me to give you this talk today. And thank you for coming and joining to hear a little bit about some recent work I've been doing on the Mowry Shale and the Wind River Basin. And I've been doing this work with my co-authors at USGS, Justin Birdwell and Paul Lillis. So let's see if we can figure out how to forward. Yeah, all right. So a little bit of background on the Mowry Shale. So it was deposited by the Mowry Sea, which is shown in this image at the right. And so the Mowry Sea was connected to the north to the polar ocean, but unlike later stages of the Western Interior Seaway, it was not connected to the south. And so this image in particular is the Mowry Sea during the early Cenomanian. And so a couple of unique things about the Mowry Shale. It's highly siliceous, and it's had somewhat of a variable age assignment over the history of its study. And so in some studies, it's been called late Albian, which would place it into the lower Cretaceous. More recent studies based on radiometric dating would place the Mowry in the early Cenomanian, making it upper Cretaceous. Over the last 100 years, there have been numerous studies documenting its hydrocarbon potential. And more recently, its regenerated some interest as an unconventional reservoir. And so the goal of this study is to better understand the conditions that led to the formation of the Mowry Shale. And so some questions that tuck underneath that are to better understand organic matter source variation stratigraphically through the Mowry Shale, to better understand the drivers of the organic richness within the Mowry Shale, so specifically how productivity, dilution, preservation effects have changed stratigraphically through the Mowry Shale and give rise to organic richness, and whether ocean anoxic event has any role in the formation of the Mowry Shale. And so the general strategy for addressing these goals and questions are we're going to look at immature source rock from 3 drill cores in the Wind River Basin of Wyoming. We're going to integrate multiple types of geochemical data, including bulk organic geochemistry, major and trace elements, mineralogy, biomarkers, as well as organic stable carbon isotopes. And so here's where we are. The Wind River Basin is located within central Wyoming, and a little bit more context in the figure down below on the lower left. We have some basins you may be familiar with in the Rocky Mountains. We have the Greater Green River Basin to the south of the Wind River Basin. We have the Powder River to the east and the Bighorn Basin to the north. And the Wind River is sitting kind of right in the middle of all those. And so a zoom up of where our drill cores are from. So they're from the eastern part of the Wind River Basin, and they are adjacent to the Casper Arch, which is labeled here. And so the drill cores are Oil Mountain, which is located to the north, Poison Spider, which is in the middle of the transect, a little bit to the south, and then we have the Alcova Reservoir all the way to the south. And just a note that the organic, we did a more in-depth study of the organic matter within the Oil Mountain, specifically looking at biomarkers and stable carbon isotopes. And so those analyses weren't performed for all the drill cores, just Oil Mountain. So the stratigraphy that we're going to be looking at within these drill cores is the overlying frontier formation, the Mowry Shale. It does, 2 of the drill cores do penetrate the muddy, although we don't sample that and do further analyses on those. And then we have some data from the Thermopolis as well. And on the right panel, we have the log correlation of the 3 drill cores. The drill cores are located or are organized north to south, and I'll be showing data from the drill cores organized in this fashion for the remainder of the talk. So we have Oil Mountain, Poison Spider, Alcova Reservoir. And again, we'll be looking at frontier formation, the Mowry Shale, which is subdivided into the upper siliceous part, as well as the underlying Shell Creek equivalent unit, which is less siliceous, but still part of the Mowry. And then again, we have the muddy and the Thermopolis. And so I always, when I do my geochemical work, I always ask myself, what's the thermal maturity that I'm dealing with here? Because that sets the stage for everything that follows, how you interpret your data and what it means. And so here is a plot showing Tmax data with depth for the 3 drill cores. Again, Oil Mountain, Poison Spider, and Alcova Reservoir. We see a very similar stratigraphic pattern for all 3 drill cores. I'll just point out that the color code throughout the talk is going to be the same, where we have frontier in green, we have the upper, middle, and lower Mowry, which are informal subunits that we've defined based on TOC, which I'll show you in a minute. And that's in yellow, orange, and red. And then we have the Shell Creek and the Thermopolis in blue and pink. And so these Tmax values are consistent with immature organic matter. They're highly variable, 20 to 30 degrees C variation in Tmax. However, this Tmax variation is unrelated to thermal maturity, which we'll talk about shortly. But we find the lowest Tmax values in the organic and hydrogen-rich middle Mowry. So that's this orange interval here. And some of the highest values in the frontier and the Thermopolis. And so we have some biomarker thermal maturity parameters from the Oil Mountain drill core, which again support immature organic matter. And so these are based on hopanes and steranes and their different stereoisomers. And so, yeah, these are indicative of immature organic matter. We don't see the same kind of variation that we do in Tmax. We do see some variation in the upper Mowry and the frontier, which is related to differences in organic matter source, which we'll also talk about a little bit later in the talk. So we'll touch on source rock quality. Here I'm showing some figures again with depth of the TOC, so total organic content, from the 3 drill cores. And we see consistent patterns for all 3 drill cores where the highest TOC values occur in the middle Mowry. And also those maximum values are also quite similar across the 3 drill cores, about 4.5%. And so this is how we've defined the informal subunits of the lower, middle, and upper Mowry, is based on these TOC trends, which are very consistent across the 3 drill cores. Next, we have hydrogen content reflected here as, or expressed here as the hydrogen index, HI values, again plotted with depth for the 3 drill cores. We see the highest HI values occurring in the organic rich middle Mowry, maximum values falling roughly around 500 to 550. And it has a similar downward trend as TOC. And so this is valuable information because these are immature rocks, we know that these are close to somewhat original values because they haven't generated oil yet. These are kind of classic plots for evaluating source rock quality, and what we see is that the middle Mowry has good to excellent hydrocarbon potential as expected. It's oil prone, it's type 2, yet these other intervals tend to have less hydrocarbon potential, they tend to be a little less oil prone, and we're gonna sort of evaluate whether that's because of terrestrial organic matter or preservation differences. So we'll touch on that again a little bit later in the talk. But we want to, what is different about the middle Mowry in that it's such a, it's a better hydrocarbon, that it has better hydrocarbon potential compared to these other units. We're gonna show you some of our inorganic elemental composition data as well as mineralogy. And so these are bar charts showing major elements for the 3 drill cores. And kind of the high level takeaway points from this slide is that these drill cores are silicon rich, so that's the blue, is the silicon abundance. They're calcium poor, calcium's pink, you see very little of that. You see a little bit in a couple of the samples, but generally it's calcium poor. The silicon abundance is highest at the transition between the upper and middle Mowry, which is occurring roughly in this interval I'm sort of touching on with the cursor. And the aluminum and titanium abundances are highest in the frontier, the Shale Creek, and the Thermopolis. They're higher there relative to the Mowry. However, we do see some of these major elements that are generally associated with clay components. We see some of that in the lower Mowry and the upper Mowry as you're transitioning out of the Shale Creek and transitioning back into the frontier. And so here are our mineralogy results from XRD, and they are very complementary to the major element data, and that we see that they're quartz rich and carbonate poor. And quartz is highest where we see a lot of the silicon, which is again at this upper and middle Mowry transition. And the clay minerals are occurring where you see the aluminum, the titanium, and so you see more of that in the frontier, the Shale Creek, and the Thermopolis. And again, in some of this upper and lower Mowry as you're transitioning out of the Shale Creek and back into the frontier. Okay, so now we're gonna get a little bit into the organic matter source and composition variation and how that changes with the downcore profiles. And so this data showing this figure are some biomarker data from GCFID, as well as some stable carbon isotope data for RMAG and saturate fractions of extracted organic matter. And so the data is consistent with marine organic matter in the lower and middle Mowry. And then a shift towards a higher relative contribution of terrestrial organic matter in the upper Mowry and the frontier. We see that in the carbon preference index, the odd over even preference, see it in the pristine phytane as well. And what we see with the N-alkane distribution, so comparing the C27 N-alkane to C17 alkane, these values are consistent with waxy organic matter, which we see in the SOFR plot, where the isotope values are plotting on the waxy non-marine side. So the biomarkers are telling us that the organic matter in the lower and middle Mowry is marine, yet it's waxy. So that's kind of distinctive of the Mowry. And I haven't seen that in many of the other marine source rocks or marine organic matter that I've looked at more generally, where it's because we generally associate waxy organic matter with terrestrially sourced organic matter. Here we have waxy marine organic matter, which is a little bit unusual, but not unheard of. In this figure, I'm showing some more organic matter source indicators based on biomarker data that we've gotten from GC triple quad. And there's a whole bunch of different biomarker parameters shown here. I'm going to just focus on two that I've highlighted in the red box. And that's pHs that are related to wildfires. And so those tend to be higher in continental material. And so you see an uptick in these pyrogenic combustion-derived PAHs from wildfires. You see a higher content of those in the upper Mowry into the frontier. And then we have the styrene-hopane ratio, which is somewhat constant during the lower and middle Mowry before dropping off into the upper Mowry and into the frontier, which is again consistent with this higher relative contribution of terrestrial organic matter in the upper Mowry and the frontier. And we get some more lines of evidence related to organic matter source and composition from the styrene distribution that we analyzed via GC triple quad. And so the C30 and C28 styrenes, so that's in this panel B, C28, we have C30 in panel D, where those are consistent with marine organic matter in the lower Mowry and middle Mowry, and then this together with the C29 shows an uptick in the terrestrial organic matter contribution in the marine and in the upper Mowry and the frontier. And together the styrene distribution distinguishes the frontier quite strongly from the underlying Mowry. My colleague Justin Birdwell at the USGS has been trying to evaluate this Tmax variation that we've seen in several source rocks, or immature source rocks, that it's not related to thermal maturity. So, you know, what's the reason behind this large Tmax variation in immature drill cores? And so in the top panel, we see a couple representative pyrograms, particularly the S2 peaks. This is where you're measuring Tmax. We have the frontier in green, the upper Mowry in yellow, middle Mowry in orange, and lower Mowry in red. And we see this you know, shift in where the S2 peak is coming out. And there's also some shift in the character of the peak in terms of kind of the edges, the shoulders of the peak, whether it's like a skinnier or broader peak. And so by applying a multivariate curve resolution analysis, Justin was able to identify two components that contribute to the S2 peaks. And so that's a high Tmax component that we'll be calling component 1, and a low Tmax component that we'll be calling component 2. And we can see how those components contribute to these representative S2 peaks shown here, where the panel B is the frontier. It's mostly this component 1, the high Tmax component, very little bit of the component 2. Upper Mowry, still a fair amount of component 1, but a little bit more of the component 2. Middle Mowry, much different in that it's mostly this component 2 with some minor contribution of the component 1. Oops. And then we have the lower Mowry, which again has like a different relative abundance of these 2 different components. And so to look a little bit more at the stratigraphic variation of these 2 components that contribute to the S2 peak and also contribute to the Tmax variation, we've put together this figure. And so the bar chart has absolute S2 values, where the brown is the component 1 abundance of S2, and then the green is the amount of S2 from the component 2. And then the scatter plot is showing the relative abundance of component 1 to the total, so the relative fraction of component 1. And this stratigraphic pattern that we see in all 3 drill cores is very similar to our source indicators for terrestrial and marine organic matter that I just showed you. And so we see that both just in the general shape, but also if you calculate correlation coefficients and p-values, they're highly related. There is some correlation with redox parameters, but although that's to a lesser degree. So we believe this component 1, component 2, these are related to terrestrial organic matter and marine organic matter respectively, although there may be some preservation component tied into that we can't quite fully disentangle, but it's a lesser contributor to these 2 components. And so just to wrap up this subsection, I'll say that this shift to terrestrial organic matter in the upper Mowry and the frontier is related to falling sea level and proximity to shoreline. And so as you become more proximal to the shoreline and the deltas and output from river systems, you're picking up a higher contribution of terrestrial organic matter in the upper Mowry and the frontier relative to the underlying middle Mowry and lower Mowry. So we'll move on to depositional redox chemistry, stratification, and salinity, and what biomarkers can tell us about those, as well as trace elements. So here are a couple of trace elements that are related to redox chemistry. These are just 2 examples, the molybdenum and uranium enrichment factors. That's what EF means. And that's basically how much more molybdenum, how much more uranium do you have in a given sample relative to an average shale. So that really signifies how much is autogenically deposited rather than coming in from some sort of detrital clastic source. And so together, these show us that the middle Mowry is the most reducing, although the lower Mowry is also quite reducing. And we see similar patterns in the 3 drill cores. And these redox sensitive trace elements are not enriched in the other units. And so the lower and middle Mowry is sort of unique in that way. These are classic plots for further interpreting trace element redox data. And so they're telling us that the middle and lower Mowry had dysoxic to anoxic bottom water and sediment conditions, whereas other intervals were more oxic. When we look at how these trace element redox parameters relate to organic richness, either expressed as TOC or S2, the vanadium chromium ratio corresponds or correlates most strongly with the organic richness of the trace element parameters. So on the left, 2 panels, we're coloring the data according to unit. And on the right, we're coloring according to TOC. And so you generally get more organic richness where you have more dysoxic or anoxic conditions. And we're gonna look at the biomarker data to see what they tell us about redox chemistry. And we see a similar pattern, and although they pick up the middle Mowry more so than the lower Mowry as being more reducing. And so we have some aromatic carotenoid data on the left. We have beta carotene in the middle. We have the C35 homohopane index. We have dibenzothiophene and phenanthrene ratio. These are all related to redox chemistry as well as organic matter sulfurization. Unlike trace elements, they tell you something about, or at least in the case of the aromatic carotenoids on the left, they tell you something about the water column conditions. And so together these tell us that the middle Mowry had reducing water column conditions, as well as reducing conditions in sediments. The Geochemistry index is related to stratification, and it shows that the water column was stratified in the lower and middle Mowry, while that stratification breaks down in the upper Mowry and the frontier. In the final panel, we have a parameter, a biomarker parameter that's related to salinity, where the MTTC values are low. Those are more saline, and that seems to be the case through the lower Mowry and the middle Mowry. And the increase to higher values for the MTTC biomarker ratio, this signifies a freshening of the water column, which really is related to becoming more proximal to the shoreline and the river systems. And then we'll talk a little bit about productivity. And so productivity is, I think, actually probably one of the harder, I guess, factors to account for. But one thing that we can look at in the Mowry is the silicon-zirconium ratio as a proxy for biogenic silica. And in the case of the Mowry, seems like a lot of the biogenic silica is coming in from radiolarians. So in that way, the silicon-zirconium ratio is a proxy for radiolarian productivity. And what we see is the silicon-zirconium ratio is peaking at this transition between the middle and upper Mowry. And we see that in all three drill cores, where in the top panels, we're looking at that ratio as a downcore profile with depth. So again, a similar pattern in all three drill cores where the silicon-zirconium ratio is seeing maximum values at that interface between middle and upper Mowry. And so that's delayed relative to the peak in organic matter. We see a similar ratio also in the barium enrichment factor, where barium is another paleoproductivity proxy. It shows a very tight correlation actually with the silicon-zirconium ratio, which gives us a little bit more confidence that these together are accurately representing productivity. And so we can look again at the silicon-zirconium content of our samples as a cross plot rather than a downcore profile, which is what we're seeing in the bottom two panels. On the left, we're seeing colored as a function of unit. On the right, we're seeing color as a function of organic matter or organic content. And so when these are positive correlated, they're following along a crustal trend. When they're negatively correlated, this is because of biogenic contribution, which is what we're seeing through most of the Mowry. And then when we look at how organic content is organized along that biogenic trend, what we see is that biogenic silica is associated with organic enrichment, expressed as TOC, but we don't see a strong ordering of organic content along the biogenic trend. So these aren't tightly coupled where you're going further along the biogenic trend away from the crustal trend and seeing an increase in organic matter content. That's not what we're seeing. We're seeing kind of more of a smattering, a spread of organic richness along the biogenic trend. And that's really consistent with this delayed peak in biogenic silica relative to when the peak in organic enrichment occurs within the Mowry. Now we're going to talk a little bit about dilution, and I'll just show you the same figure because this is also related to dilution in that this is a biogenic component that dilutes the organic matter, right? These are hard parts from zooplankton that dilutes the organic content. And so this positive correlation of biogenic silica with organic enrichment is the opposite pattern that you'd expect with a dilution trend, where usually with a dilution trend, you would expect to see more of this hard part, more of the biogenic silica should dilute out the organic matter. So it would be an inverse trend. So in this case, we're seeing the opposite. So the Mowry is enriched in organic matter kind of despite the biogenic silica dilution factor. But then we have clastic sediment that we need to account for. And so in this panel, I'm just showing two proxies for clastic sediment supply, aluminum in the top, rare earth elements, the total abundance of rare earth elements in the bottom. And again, for the 3 drill cores. We see very similar patterns. And what we're seeing is that you have the minimum clastic sediment supply occurring again at this interface between the middle Mowry and the upper Mowry. And so there's a delay, there's an offset with where the organic enrichment is occurring. So it's happening after the peak in TOC where you get the minimum in clastic sediment supply. And this is consistent with what we see in the clay mineral abundance trends from XRD. And so I will touch a little bit on whether we have any isotope evidence for whether an OAE, an ocean anoxydant, had a role in the deposition of the Mowry, and in particular its organic richness. So there are a couple of papers throughout the history of publishing on the Mowry that have mentioned that it may be associated with an OAE that occurs at the end of the Albion. And what they're actually quite, there are very few stratigraphic records of isotope data from the Mowry. And so here I've presented, this is all from Oil Mountain. I've got bulk organic matter C13 data, as well as C13 data for saturate and aromatic fractions of the extractable organic matter. And in these 3 profiles, what we're seeing is a negative carbon isotope excursion in all 3, followed by a broad positive isotope excursion through the remainder of the Mowry before dropping off into the frontier. And this is actually somewhat similar to the general description of what we see for the OAE-1D, which is the ocean anoxydant that's occurring roughly at the late Albion, possibly into early Cenomanian. To my eye, it's not a very convincing carbon isotope excursion pattern. The Albion-Cenomanian boundary, based on recent radiometric dating, likely is occurring in the Shell Creek, so underneath the Mowry. And so, there's not great age control, in my opinion, on the OAE-1D, but just based on the carbon isotope downpore profiles, I would say that this suggests that the Mowry probably postdates the OAE-1D until we get better age control on the OAE itself. And so to summarize, I've put together this schematic where I'm showing the downpore profiles of organic matter richness, preservation, production and dilution, right? Because in this case, biogenic silica is sort of tied to both. Dilution from clastic material, as well as organic matter source variation. Just based on the stratigraphic profile itself, as well as sort of a more rigorous analysis of correlation coefficients and P values, so kind of the significance of those correlation coefficients. Preservation is most closely tied to organic enrichment within the Mowry. Although, clearly production is a part of this. We have reasonable production during the middle Mowry when the TOC peaks. And we have reasonably low clastic contribution during that middle Mowry where the TOC is peaking. And it's marine organic matter in origin. So, all those are in line, but if you look at, what is kind of marching more lockstep with organic matter through the Mowry, preservation, particularly, that's including kind of, reducing conditions, but also the sulfurization of the organic matter itself, which is, a really kind of high power additional factor for preserving organic matter. We're seeing that is more closely tracking the organic content within the Mowry. So this is not to, rule out production or dilution as other important factors. They're clearly important and required, but yeah, redox is, you can't overlook that in terms of what's driving organic matter richness in the Mowry. And so there's definitely some similarities, I would say, in terms of the Mowry to the Black Sea. You know, it's a restricted basin. It is anoxic. It's stratified due to some freshwater contributions from deltas. It's also distal, which is important for the amount of dilution that it sees. So with that, I'm going to acknowledge a lot of people who have helped us get this work together over, I don't know, a couple of years now. So Zach Holland and the USGS Core Research Center for giving us access to sampling these cores. And I'll just note that the oil mountain and the poison spider cores are both at and currently available at the CRC. The USGS Petroleum Geochemistry Research Lab for their lab support. Tom Finn is another colleague at the USGS who has been working on the Mowry, has offered valuable insight and discussion about the Mowry, as well as helping us to prepare the map and cross-section I showed you earlier. Zach Holland and Alexa for, again, valuable discussion on the Mowry, since they've both done their thesis on the Mowry. And then the Energy Resources Program at USGS for their funding support. And with that, I will just take questions.
Thanks, Kate. That was really insightful. There are some questions here. They're in the chat box, and I'll read them off to you.
Okay.
Justin kind of stepped in on a couple questions here, but to support. But Neil Fishman was wondering, were the Tmax values determined on samples that were cleaned to remove solvent extractable to exclude the S2 shoulder from the pyrograms?
Yeah, thanks for asking that question. Yes and no. So we did it both ways, right? In some senses. So for poison spider and for alcova, we didn't do any extractions on those. And so that's whole rock. For oil mountain, we compared both. So we had the unextracted Tmax values, and then we had, after doing the extracts, we reran those. And so, yeah, the data is actually quite similar on oil mountain between those two data sets, between the ones that were run as whole rock and the ones that were run after solvent extraction.
Okay. Ron Parker had a question regarding the silicon enrichment and why the Mowry is anomalously silicon enriched. Is it planktonic organisms, and how much can it be attributed to volcanogenic input?
Yeah, so that's actually one of the, another kind of side project that we're working on. And let's see if I go back to that slide. Oh, here we go. Yeah, so this crustal trend is based on average shale values from publication in the mid-90s, Wedpol. And then if you look at volcanic composition, they tend to be in this kind of space, so to the right of the crustal line, so higher zirconium values. Although there's quite a bit of variation, and that's important for a lot of source rocks we see within the Western Interior Seaway, where you have a lot of bentonites, whether volcanic material can be contributing silica or zirconium. But in this case, this biogenic trend that we see is, I think, pretty well tied to a biogenic source, particularly radiolarians, just based on, I guess, more, microscope work where we're looking at the rocks in greater detail, right? Radiolarians seem to be a big contributor. So it's not that surprising that you have this biogenic trend. But yeah, some of these values out to the right of the crustal line may be related to a volcanic source. That answers that question.
No, I think that does. I haven't seen some of these plots, and that was really interesting to understand that.
Yeah.
These are really powerful plots. Terry was wondering, are there differences between Upper Mowry and Lower Mowry regional? Do you expect them to hold in the similar trends that you saw in your three cores, does
Yeah.
that change between here and the Powder River, or?
I think that's it. Yeah, I mean, that is a good question. It's definitely, I think the trends that you're going to see are going to change based on proximity to shoreline. In this case, the Wind River is intermediate to distal. Of course, that's changing stratigraphically, right, as sea level's changing. But generally, they're intermediate to distal environments. And so I expect that there may be some differences if you're in a more proximal location. I think that these probably behave fairly similar to other distal environments where the Mowry is deposited. And that's just based on some comparison of these data with data from BOHAC's 2005. They seem to behave similarly to the distal settings that they evaluated in that publication. But yeah, there may be some different behaviors you would see in a more proximal setting.
Another question from Ron here regarding the elevated silica in the Mowry. Why does it lead to a more chert formation? Is it just the radiolarin? Were diatoms a contributor to the biogenic silica?
My understanding that diatoms could be contributing some, although they're not the dominant. I can't really comment on the chert formation, just because that is not my area of expertise of what leads to chert genesis.
Okay, another question from Jeff May here. Was the geochem of the Mowry Sea itself unique? He goes on to say, fish scales and bones are prevalent and well preserved throughout the Mowry versus the Shell Creek and Belfouche/Frontier.
Yeah.
How does this phosphatic material affect your analysis?
How does phosphatic material affect the analysis? Well, my understanding is that barium is associated with material like fish scales that you've talked about. And so that may contribute to this barium stratigraphic pattern. We have phosphorus data, and generally it's fairly, I would say, scattered. And so, yeah, it may just be that based on our sampling resolution, we're not seeing kind of cleaner patterns in the phosphorus. Is it unique in its geochemistry? I mean, I guess there are other siliceous source rocks, but the siliceous nature makes it a little bit different than, the Eagleford or the Niobrara, carbonate source rocks where, organic matter sulfurization may be a more prominent feature than in the Mowry. So yeah, we can talk a little bit more about that question about what else might make the Mowry unique. But I think it has some similarities to other source rocks that were also deposited in a restricted environment. Maybe in a more distal setting, like there's some similarities there. But yeah, I think the siliceousness versus maybe carbonate richness distinguishes it from other source rocks in terms of how the organic matter sulfurization may be working.
There's another question regarding the Black Sea analog, and I guess maybe just a comment, but somebody thinks that the Black Sea is a lot deeper than even the deepest estimates for the Mowry. I guess, do you think the Black Sea is still a good analog?
I think that's a really good point. I think a lot of these epicontinental seas that we see, more deep time than modern, tend to be shallow, right? There's been, historic, professional debates about water depth in, ancient systems. And I do tend to think that they're more shallow than maybe we sometimes think. And so, yeah, that could be a distinguishing feature with the Black Sea. I'll have to confess, off the top of my head, I don't know the deepest part of the Black Sea, how deep that is. But no, I definitely take that point, because in general, I tend to think these continental seaways are potentially more shallow than we think, and whether we have a good analog for that in the modern, not clear that we do. I mean, the Baltic Sea may be another, it's fairly shallow, but yeah, maybe still even more deep than what we're seeing in some of these ancient Cretaceous seaways.
Yeah, the Cretaceous sometimes feels like a bathtub.
Yeah, I think so. I tend to think that.
Yeah.
But
another question from Ron Parker regarding Jeff May's question. This getting deep into the geochem here. It's over my head. Phosphates are sponges for uranium. Would phosphate enrichment alter the uranium redox proxy?
yeah, potentially. I mean, we see there can be some similar behavior for uranium and carbonates where, if you calculate an enrichment factor in a carbonate, you're assuming that a carbonate has 0 uranium, and that may or may not be true depending on the kind of carbonate you're looking at. And so that's kind of parallel to how an enrichment factor is calculated if you're not accounting for that kind of absorption with a phosphate-rich interval and an enrichment factor. And so that could be happening, but that is, I think, kind of the power of the data set, and where we're not just looking at uranium, we're not just looking at molybdenum, we're looking at a set of trace elements, but in addition to that, we're also looking at biomarkers that don't have that kind of behavior. So yeah, no, I mean, you see that's one of the weaknesses of enrichment factors, is that you're assuming that all of that element is either associated with a classic, detrital source, or it's authogenic. And so something like a phosphate-rich, I guess, mineral that has that kind of behavior with uranium may throw a calculation enrichment factor off a little bit.
Another question here. Have you or do you plan to compare other biosiliceous source rocks, such as the Monterey Miocene or even Moreno Cretaceous of California? Are you planning to compare those other biosiliceous source rocks to the Mowry? And if so, are any of these correlations unique to the biosiliceous versus biocalcareousness?
So I guess we have thought a little bit about exploring particularly the silica and zirconium patterns in other siliceous source rocks, comparing that to other carbonate-rich source rocks, or more clay-rich source rocks, different lithologies. So whether we're going to look at those specific source rocks as a comparison to the Mowry, I think we may. I mean, it sort of depends on data availability. But yeah, there's certainly plans for that with regards to this biogenic silica, silicon zirconium cross-plot pattern. So yes, I would say hopefully in the not too distant future.
To be determined, right?
Yeah.
I see Dan Jarvie to everyone. Kate, any visual kerogen data to support the mixing of terrigenous and marine organics?
Yeah, great question. We don't have any of that data on these drill cores, but one of the very few publications that have some stratigraphic biomarker data was from Dahl et al. 1994. So there are other papers that have biomarker data for the Mowry. Some of it's from oils, some of it lacks some stratigraphic context, which we're hoping that we've achieved here. But this paper from Dahl et al. 1994 was further west from, I believe, sort of western Wyoming, Aspen Shale, so Mowry equivalent, and they had kerogen data, and they were able to show how the amount of vitrinite or the amount of amorphous organic matter in their petrographic results relates to biomarker data, some of which I've shown here. And so I think those relationships probably also hold here, although, because, Aspen Shale is, a Mowry equivalent, it's not too far from our study site. So I think those relationships probably hold here, but we, in this case, don't have any petrographic data for these drill cores directly.
I don't see any other real questions here. I think there's just some general commentary here in the chat box that there are many marine source rocks in the Paleozoic, especially in the Paleozoic, that are silica rich, biogenic, like the Marcellus, Horn River, Barnett.
Yep, yep. So some of those are on our radar screen also for this kind of specific topic area. There's even one in the Neoproterozoic, which I have some interest in just based on my previous work in the Precambrian. So yeah, I mean, there's a lot of other silicious source rocks that we're hoping to draw some comparisons with the Mowry. Maybe not for the full data set that we've put together here for the Mowry, but specifically the silicon zirconium story. So yeah, we are definitely hoping to collect Marcellus and Woodford and Barnett data as a comparison for that.
Yeah, well, Kate, I think that's really it for the questions. We really appreciate your talk, and RMAG thanks you. I thank you, and I think that was really an awesome talk and really insightful, and glad you were able to do it.
Well, thank you again for the invite, and if anyone has any questions about what we've talked about today, don't hesitate to email me, and we're hoping that we're going to have this submitted and out for you guys to look at your during your own time. Hopefully soon it will be out. So
awesome. Well, we